Good evening. In this tutorial, we will speak the setups that used in the testing of the membranes in the lab scale. And I try to show some this apparatus. You know that the flow regime on the membrane surface can be in dead-end model and in cross flow. And as discussed, in most industrial application, we have this regime because the fouling in this scale is lower. But in lab scale, in most use the dead-end system for testing of membranes, because if we want to use the cross-flow cells for fouling test, we should today's test membranes for fouling. But in dead-end, with 1 hour, 2 hours, membrane mostly fouled and flux reduced, and therefore we can rapid test the membrane, and the fouling ratio, fouling amount in the dead end is very higher than the cross flow. And if we have a good flux recovery ratio in dead end, we can see we have very, very better performance in cross flow. For dead-end test of microfiltration, or all of porous membranes, we have these similar cells. You see, this is the open of this cell. This cell have 2 sections, bottom and top. This is top section. This is bottom section. And you see, we have an orange, elastic orange for sealing. We get out this orange and put the circle membrane on the surface of this porous medium. This is a Zinter filter. Zinter. We have a very big pore size and usually used as a gas filter. In some valves, entrance of valves, this Zinter filter is a support for only keeping of the membrane. We put the membrane here. We put next this tubular, that this tubular here is from plexiglass, from a plastic, but for high pressure we can use the metallic one, stainless one, and put this section on the top of this, and these tubes go from these pores, and we close them, and we have this. We have a styling. We have a magnet inside of this part, and we put the dead end cell on a styler, and this styling remove or reduce the concentration polarization. We want have a real conditions for test, and this agitation, this stylation, reduce the concentration polarization. This magnet come 1 centimeter top of the membrane and mix the direct top of the membrane. This is a general cell. We have a gauge, pressure gauge, for showing of the how many pressure applied, and we have a tube that the entrance of the feed. This is connected to another tank, and usually here have 100 to 300 milliliter volume. We have one feed entrance, and we have a permeate entrance. Permeate here collected from a beaker or cylindrical device. There are different forms of these cells. As you see, all of can be plastic, or here plastic, here metallic. This is a schematic of the setup. The dead end cell is here located and connected with a tube to the main tank. And for applying up pressure, we usually use the nitrogen tank. Have a regulator that can reduce the pressure and apply 1 atmosphere, 2 atmosphere, usually up to 10 atmosphere. We use this device up to 10 atmosphere test. And the permeated can be weighted or can be volume is measured. This is the usual schematic of a dead end setup. This is another picture. Here, the main, in the previous slide, the next slide, we can see that some cases the main tank can be steel, stainless steel, or here have a plexi and come here, measure the pressure and the permeate collects on the balance. This is all steel. This all steel and used for high pressure, and this is the steering magnet. Or here you see that for continuous measurement, the balance is connected to a computer, and no need to student stay here. After preparation all of things, automatically weight the collected permeate. You see, both the tank, stainless tank, is connected to a cylindrical. We can use, instead of cylinder, we can use a compressor. We can increase the pressure with compressor and no need to nitrogen. These are my setups in Iran that have a, because the error of membrane is high. And for reporting of one data, we usually give average of 6 tests of membranes. After giving of the 6, we give the average and report data. Therefore, very time is needed. For reducing of the time, 4 membranes in a simultaneous time test for increasing of the efficiency of the group. Or in this case, you see, one student work with this, another with this, and test the membranes. Another setup is cross-flow. We use cross-flow mostly for RO and nanofiltration membranes. If we have a low pressure, use the plexiglass one or polyethylene one. If we want to test organic resistance nanofiltration, that we separate some pollutants from solvents, organic solvent. In this case, the material is PTFE, polytetrafluoroethylene. This is for RO, for high pressure, 50 atmosphere pressure. In this case, we have a very secured system. In the cross-flow, you see in the dead end, we only have a feed and permeate. But in the flow, in the cross flow, we have a entrance for feed, permeate, and concentrated. Okay, one feed come and divide to two stream, one concentrated and one permeate, and we measure the entrance pressure and exit pressure and give average for reporting of our applied pressure. When we say our pressure is 10 atmosphere, this usually is 10 point. This is the 9.5. 10.5, this is 9.5. Usually we have a pressure drop in the system. Therefore, the entrance and exit is difference. This is a graphical design of the cells. You see that the cells have two parts, bottom and top section, and the membranes is located in this area that show that feed come here, pass from the membrane surface, and as a concentrate go to the tank. And for sealing, we have a two O-ring that seal the membranes. This is a simple test of the cross flow. This is our cell. One here is entrance of the feed, and this is go to the concentrate. And we have entrance pressure and exit pressure, and with control of these valves and these valves, we can control the flow and pressure. When we want to control the flow and pressure, the pump is began to work and circle the water, but with closing of this valve, we can increase the. When this valve is completely open, we have no pressure. When we begin to closing, the pressure increases, and this is a bypass. And with this bypass, we also control the flow of the membrane, flow of the fluid that pass from the membrane surface. This is my cross flow setup in Iran, and you see for repeating and increasing of tests, we have three parallel cells for continuously test of three membranes. You see here, we have a high pressure pump. Here is the tank. We put feed here. From this tube, go to the pump. The pressure increases and insert the first cell, second cell, and first, second, and third cell. And in each section, we measure the pressure for controlling the pressure. This electrolytic system can cause to the increase of the pump rotary, and we have a temperature control. This is the temperature system. We have a cooling system in the tank. With working of the pump, the temperature of the feed increases, and for reducing of the temperature, we have a stainless steel foil that entrance cool water and decrease the temperature. Therefore, in feed tank, this tube you see, cool water come and hot water go. Therefore, we can control the temperature. The cross-flow systems, our cells, this cells is a what is said to for angle? What is? Not circle. What is this for in English? Rectangular. Rectangular. But some cells can be prepared in circular form, as seen. In this area, in the rectangular, we cut, for example, mostly 4 in 10 centimeter. But in this circular cross flow, we cut as a circle, and here is entrance of the feed, and here is exist of the feed as a concentrate. And when here entrance, go to the all of the circle, and in all of the area can come to this central tube. Therefore, we have a cross flow on the membrane surface. This is a clamp for keeping them together and obtaining them. Some circular cells also, the effective area can be rectangular. This is also another cross-flow system. Osmonics setup system is very expensive, this one. And this another schematic in lab with rotometer. This is a rotometer for measuring the flow. Another pressure cell, another. Oh. Is there any question about dead end and cross flow? Everything obvious? It is possible, no. I want to draw a figure. It is possible this go to the top, I write here. This go. I want use this. This go to the top, can collect.
Actually, what happens that it will not record, no? It will record.
Cannot sound?
Actually, what happens, their camera resolution will not be very
Okay.
good if we write. So
Okay.
what you can write, sir, on the white part.
I wanted
to
to-
give you a slide.
One second.
Blank. You can write it.
Okay. I want this here. Okay. Thank you. For membrane test, for example, we want test a UF membrane. After preparation, we have a 4-step test for membrane. We first measure the pure water flux, how many the flux of this membrane, and in the second, we usually fold the membrane for showing that this membrane, how can be fold. And after that, we measure the recovery of membrane. This membrane, how recover there after falling. And we use the washing for the membrane. And in the 4 steps, we test the rejection ability. rejection ability for protein, for dye, for heavy metals, and our target pollutants, okay? Therefore, we have usually this diagram. You see in more papers that this is a time and this is the flux, okay? First, we measure the pure water flux. For example, this is the 2 hour. In different time, every 10 minutes, based on the membrane flux, 20 minutes, we measure the volume of the water, and we know how membrane surface, and with measuring of the volume and area and time, we report our flux is here with pure water. Here is pure water. Okay. In the second step, we replace the pure water with foulant agent. Foulant agent can be oil based on the wastewater, can be our wastewater. We have a industrial wastewater and replace our pure water, distilled water with our wastewater. The standard solution is bovine serum albumin. Bovine serum albumin, a protein from cow, BSA. In the most cases, for comparing our results with literature, we must use the BSA with this concentration. What happened? With this concentration, when we put the BSA in the dead end cell or cross-flow cell, BSA attaches to the membrane surface and reduce the flux. We have this, rapidly reduce. And we usually test 1 hour, 2 hours the BSA. This is the BSA flux. With a standard solution mostly, but we can use other foulant. And after 10 minutes, 20 minutes, we reach to the stable one, okay? Now, we separate the membrane from the cell and wash only with water. Only with water. We want to say that our membrane, how is resistance to fouling? How can recover their properties with washing? We usually do not use the cleaning agents such as acid, base, water. After washing, 20-minute washing, usually with water, we measure the membrane pure water second. We say second. Second flux. Okay? Second flux. With this data, we can calculate the membrane intrinsic resistance, membrane resistance to gel layer, membrane resistance to pore size fouling, and others with this simple test, okay? If our membrane is very good, this flux should be here. This show after falling and cleaning, the ideal membrane is that this come to here and go this. But our membrane have not complete recovery. We can calculate the amount of recovery. We name this one as G1 protein flux and G pure water 2, okay? Now we can calculate the parameters, which is one is the sealer. No. We have the first question. We test the membrane with pure water, okay? Why flux reduced? During the time, our flux reduced to this one. Is there any foulant in distilled water? We have tested the membrane with only pure water, distilled water, no salt, no any. Why flux is reduced? That means the membrane is followed. Why happen? Due to the compaction. Due to the compaction. Oh. When we apply pressure, membrane began to compaction. Oh. For reducing the compaction effect, we before this point, we usually test the membrane with pure water with higher pressure. If our applied pressure is 2 atmosphere, before beginning in this area, we apply 1 atmosphere higher pressure. If our applied pressure is 2, we use 3 atmosphere for 30 minutes for compaction, good compaction. After that, reduce the pressure to 2 and start this point. But we have now the compaction, and this compaction is every time. After 10 days, maybe it reaches to the stable, but we see that here is sharp, but reach to the steady state. Therefore, after that, we have a compaction. After this one, we can calculate the fouling parameters, FRR, flux recovery ratio, that is the flux of second pure water to flux of the first second. If the flux of second and 1 is the same, we have 100 FRR, that it is ideal. We cannot reach to this usually, okay? We have 2 fouling parameters also as a reversible fouling ratio, reversible fouling ratio, and irreversible. Okay, fouling ratio. reversible with test of the protein, okay, the pressure is reduced, the flux is reduced, and after washing, this amount is recovered, reversible, okay? This amount is reversible. This amount I show with other color, maybe. This amount is reversible. But this amount of flux is irreversible. Therefore, we can calculate the amount of reversible and irreversible that calculate as this. G dou minus GP to G1. Irreversible, this amount GW1, GW2 to G. Okay? And there are another equations that I will speak tomorrow in the following section. We can calculate intrinsic resistance, cake layer, and pore resistance, and others. Usual test with UF, MF, NF is this test in the lab with the shown setups. And in every test, when we want to measure the salt rejection, dye rejection, every rejection, we first compact pure water flux, and after that, we use the separation, heavy metal solutions replace, okay? But we have two series, one series for BSA fouling test, and second for separation test. Okay. We can go to the slide. For hollow fiber test, the process is similar. In hollow fiber test, we can also test as a dead end and as a cross flow. We have this usual setup for hollow fibers, you see, such as this also, you see. We can prepare from stainless or from the plastic tubes. That, for example, the feed can be here, go here, and as a concentrate, get out, and the permeate can collect here and here. In this case, we have a cross flow. Feed come and concentrate. But if we close this exist here, we close, we only have a feed and only permeate. Therefore, when we have an open here, we have a cross flow. When we close the concentrate section, we will have a dead end section. Such as the flat sheet setups, we have a permeate tank, we have a feed tank, and usually we use the peristaltic pump for applying the pressure. This shows the flow of the this solution. And here we can see the applied pressure. For ceramic membranes, also we prepare this similar to the hollow fiber modules, only we have a one tube here. Okay, we can plastic tube or ceramic tube. For sealing, we have an O-ring, the similar one. The feed come here and exist from as a concentrate, and the permeate can be go here or reverse. Feed can come here from concentrate, and we collect the permeate in this case. That means the feed can be outside of the membrane or can be inside of the membrane based on the active layer of the tubular membrane. This is a setup of the ceramic tubular membrane with a length of 1 meter. We have a pressure gauge for entrance, pressure gauge for concentrate, this valve for control of flow, and here we collect the permeate. This is a tummy ceramic membranes that sell 10 membrane with a pressure vessel. You see, this is a pressure vessel. And such as them, we can put the membrane here, add the black O-ring here, put them with this clamp, and test the membranes. One of the important parameter in the filtration membrane, MF, UF, and NF, is molecular weight cutoff. Molecular weight cutoff measurement. For measurement of the molecular weight cutoff, we usually use 5 or 6 different molecular weight of a component, such as polyethylene glycol, such as starch, such as dextran, such as glucose, saccharose, and others, okay? For ultrafiltration, we use the big size of the polyethylene glycol. For drawing of this diagram, we need at least 5 and 6 points. For example, this kilodalton, we select polyethylene glycol. Polyethylene glycol have a molecular weight from 200 to 2 million Dalton. Okay? Therefore, we first select one solution and see that the rejection of this molecular weight is low. The second molecular weight, the third, 4, 5, 6. We 6 times test our membranes with different molecular weight solution. If we have a HPLC, we can mix all polyethylene glycol with different molecular as a one solution and measure. This is very easy, but usually we have not HPLC. Therefore, we test separately so we have prepared 6 different solutions and began to test the membranes. With having of these 6 points, we draw this diagram. For measuring of the molecular weight, we see that the points can reject 90%. Therefore, after drawing of this diagram in the Excel, we draw this line to the cut the diagram and go back to this one. And this place will be our molecular weight cutoff. if we go to the commercial membrane sites, you see that there are maybe 20 ultrafiltration membrane with different molecular weight cutoff. Say I have a UF with molecular weight cutoff of 50,000, 100,000, 200,000, and this molecular weight cutoff is showing the pore size of the membrane, and it is reality than the other processes that yesterday I discussed. This is a real test. You test with a solution and obtain this data, and this is very real. Another setup is dialysis or forward osmosis membrane, or membrane distillation membrane also. In forward osmosis, membrane distillation and dialysis, hemodialysis, we have the solution in the permeate site. In the UFMF, as you see, in our setup, the permeate goes to the weather. But in this membrane processes, we need two pumps instead of one pump because we have a two stream. One stream as a feed, one stream as a receiver. Receiver in the permeate size. In dialysis, hemodialysis, membrane distillation, we must have a flow in the permeate site. Therefore, you see, we have a two pump, two tank, and if this tank is feed, come to feed side and get back to this one. Okay? And for this one, we have a pump. Therefore, one pump is for feed side and one pump is for permeate side, as you see in this schematic. For MF membranes, for separation of oil, water, we usually, the best membrane is gravity-driven membrane. That means in this scale, we have not pump. Only with low pressure, now, when we have a 1 meter height of water, 1 meter, this is equal to 1.01 atmosphere. 10 meter water is 1 atmosphere. Okay, you know. Therefore, in this height that is mostly 30 centimeter, not very high, with very, very low pressure, gravity-driven pressure, due to we have a very big pore size. For example, if the membrane is hydrophobic, oil pass and water not. If the membrane is hydrophilic, water pass and oil not. In the YouTube or in the supplementary information of the oil-water separation membranes, you can see many videos that pour the water here and rapidly oil separate from the water. For testing of this, we usually have a similar setup. If we need a little vacuum pressure, this is can be connected to the vacuum also, if we want to apply very low pressure. Membranes are located here. This section separate from membrane located here. You see this membrane, and this clamp keep the membranes. This is a MBR, membrane bioreactor system. In the MBR, we have a activated slot tank. that there is a microorganism there, and we give oxygen, aeration for biological degradation of the organic pollutants, and give some foods, some vitamins, some ingredients such as zinc, magnesium for growing of the microorganism, because microorganism is live and need food. Without carbon, need the mineral also. For separation of the microorganism from treated water, we usually use immersed microfiltration or ultrafiltration. Usually similar setup is used. You see have some suction pump. This is yellowish, usually filled with the aeration tank. And maybe we can have anaerobic, without aeration. This usually aerate, and with usually non-aerate. I have a video we can show. Please show video. MBR system. This is a MBR system in a Turkish lab. We have a feed tank and permeate tank. This is a control system. Aeration of the sludge, and the membrane is immersed. Them and suction can take with this valve. We have a, please repeat again. We have a 3 pump, 2 pump for feeding, one feed, one not other minerals for growing of the microorganism, and one pump is for suction of the membrane. Okay. The second film, dead end, no, video. Dead end. This is one of the hours in Iran for parallel. This styling reduce concentration, polarization. And the permeate come from this blue, the applied pressure, 3 atmosphere. And we measure the volume with this cylindrical. Okay. In some cases, we need to measure the diffusion of a molecule or ions from membrane and measure that this membrane how diffusion efficiency is dialysis cell most used. In this case, we have similar system that membrane is located here, and with this clamped or closed, and one side is feed side, and other side is receiver side. We put feed here, and after our every certain times, sample from the receiver side and measure the concentration of diffused ions. If we have a salt, measure the conductivity. If we have a molecule, we give the TOC, COD, or UV spectrophotometer for measuring. Therefore, this is a diffusion systems used in forward osmosis, dialysis, membrane contactor, intrusion membranes, and others. This is also another one. We usually locate this device on the stirrer, and we have a styling for uniform dispersion. Therefore, these systems located on the stirrer surface. Another system is gas setups. For testing of the gases, there is two methods. Say constant volume, constant pressure. We have a two method for testing of the gas. Constant pressure, constant volume. Constant pressure, that means we apply, for example, 5 atmosphere pressure in the feed side and measure the flow of the gas, such as the liquid membrane. This is named as a pressure constant method, and usually the flow of the gas can be measured with bubble flowmeter. In bubble flowmeter, this tube will connect to the permeate of membrane, and we have here a soap solution. We pressing of this, one of the soap bubbles come here, and the gas carrier the bubble. When reach to here, that is reach to here, that is have a number 0. Reach here, we began the timing. And this bubble go here, and after reach to here, we measure the time. For example, for passing of 10 milliliters, we need 10 minutes. And with giving of the volume and the time, we obtain the volume of permeated gas. This is a simple method. We have digital one of this, digitally measure and report as a number, and different time. This is the pressure constant. And the second method is volume constant. The data of volume constant is better, and in the most cases request to report volume constant. In this method, as you see, all of system is located in water. Because I said that in the gas separation membranes, the temperature is very important. And we locate all of the system immersed as a water, and we control the temperature of water. Or we can locate all of systems in an oven, such as this. In this setup, we have an oven, and all of these systems located in this oven, because temperature is very important. With change of 1 centigrade, the permeability will change. The membrane is located here, and we have a tank here in our system, in Iran. And we can have different gas, methane, nitrogen, argon, oxygen, every gas. And the capsule is connected to this tank in the water, and the temperature controller, and come here. And in this cell, we have a membrane. We located the membrane. And these blacks are pressure transmitter. All our pressure is measured, and we can see in this plate all of the pressure and temperature. Okay, after passing of the gas in the constant volume. We know the volume of this section, and you see we have a very narrow tube. This is narrow tube. Because the permeate is very low, our surface area is 3 centimeters. Therefore, we use very narrow tube, very small diameter tube, that we can, our system was sensible. And with the pressure is constant. No, the pressure here is constant, but pressure here is this 0 time is 0. And with increasing of the permeate, the pressure began to increase. And we measure the increase of pressure in the permeate side. And all of systems is connected to a laptop, and we draw the change of permeate side. Also, as you see, in this setup, we have a left system and right and left. You see better. This is the permeation measurement. This is for measurement solution coefficient, adsorption coefficient. In the previous lecture, I said that in gas separation, solubility and diffusivity is important for measuring that this polymer, how like to adsorb these gases. We have this system. In this system, we have a very little dish, usually 1 gram polymer we put in this dish and locate in this system and contact with the gases. For example, very low pressure gases, for example, this, right? Locate 1 gram polymer in contact with 0.5 atmosphere, for example, carbon dioxide gas, and give time, 5 hours. And the polymer, if good had interaction with carbon dioxide, began to adsorb the gas from the gas media, and therefore pressure reduced. After reaching to constant pressure, we every hour check the pressure. Pressure reduced to after constant condition, for example, reach to 0.3. That means 0.2 atmosphere carbon dioxide was adsorption to 1 gram polymer. Therefore, we can calculate the capacity of gas adsorption on the membrane surface, and there are some equations. We can calculate solubility diffusion. In this system, we measure permeability. In this system, solubility coefficient, and from minus of the solubility from permeability, we can calculate diffusivity coefficient. Okay? Therefore, we calculate both solution and diffusion coefficient. This system is simple, but gas test is very expensive. The liquid test is easy. But this system, I say very simple, but you see not simple. Every of this transmitter is expensive. All should be steel, stainless steel, and others. But this gas setup is in a petrochemical company. I have a big project with them and fabricate this setup for mixing of gas. We have a different pressure gauge, different mass analysis setup for measuring the mass flow, and very, very expensive setup this for gas separation. Thank you. We have a video, show the video, and our presentation finished. If any question about the setup? We have a pervaporation setup, membrane distillation setup, dialysis setup, bigger one, but no time to show. We have a minute. A video, please. Video. For showing the entrance of the gas setup. Yes, gas. The video of this gas. This is better, huh? This is the water tank. These valves is used to vacuum. Before testing, after keeping the membrane, we vacuum the system for zero pressure in the permeate side. After the vacuum, we began to test. From capsule, the gas come here for control the temperature, and next come to the entrance of the membrane with opening of this feed valve, feed pressure. This is the cell, and this is the for vacuum. This is the permeate side. Permeate side come here. We have a very little tank here, and measure that. This is a very sensitive pressure. And if during test, here we have, for example, 5 atmosphere. If during test the membrane is tear, is poor, this transmitter will be destroyed. Therefore, the membrane should be very good stability. If no stability, because very sensitive, this sensor will destroy. This is, we have a 2 O-ring for sealing of the system. The effective diameter is 3 centimeters because the gas polymer is very expensive. We do not test the big one. We want to use the lower amount that reduce the expense of experiment. This is the adsorption. We have a very little dish. We put the 1 gram polymer here and put them in this one. Control of temperature, heat the tank, feed tank of the water, and this circulation pump circle the water in the system for controlling of the temperature. Feed pressure, permeate pressure. This is sorption section, feed sorption and downsorption. If any question, please. Elektrik sistemi diyorlar. We have a USB. This USB can be connected to laptop for recording of the data. All measured pressure can be recorded in a laptop. Thank you. Any question?
Any question from the audience side? No question?
No question.
Okay. All the videos and the explanations that you were saying, it was very fascinating to me, especially about the gas separation. So these were very exciting. I hope some of us will get a chance to work on such kind of systems on by hand in a near future. So I thank the professor for his enlightening lecture today. So next, what we have is a tutorial. It is about some practical problems as per the schedule, some practical problems related to the membrane filtration setup. Okay. So shall we take a 5-minute break and start, or shall we start right away? Break? Okay. So let us have a 5-minute break, short break, and then we will gather back here to restart the session.